Hello and welcome to the Daily Space. I'm your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we are here to put science in your brain.
This week, the planetary science community is gathered together virtually, sharing all their latest results about worlds near and far at the Lunar and Planetary Science Conference. Later today, we'll be discussing news about Mars water and one of my favorite topics and Pamela's favorite topics, volcanoes, here and on other worlds.
Not all the news, however, is limited to planetary science. In our lead story of the day, astronomers have begun to resolve the structure of the universe in a level of detail previously only seen in simulations. Thanks to the observations of bright quasars, we've been able to trace out the vaguest outline of the cosmological structure of the universe for some time. But those bright systems are rare and don't really show any detail on what is going on. Now, using 140 hours of observing time on the 8.2 meter Very Large Telescope in Chile, astronomers have peered into the faint details of the large-scale structure and resolved a sea of previously undiscovered small galaxies, shown in blue in this image. According to study co-author Jope Shakai, we think that the light we are seeing comes mainly from young galaxies, each containing millions of times fewer stars than our own Milky Way. Such tiny galaxies were likely responsible for the end of the cosmic dark ages, when less than 1 billion years after the Big Bang, the universe was illuminated and heated by the first generations of stars. So far, only a tiny fragment of the sky has been seen. But the researchers behind this work are working to improve the camera they're using on the VLT so that it can capture 2 to 4 times more of the sky in its field of view. This work is being published in Astronomy and Astrophysics and was led by Roland Bacon.
Looking into the first moments of the universe isn't easy. And sometimes it takes more than just a massive telescope and countless hours of observing. Sometimes you have to actually figure out how to use gravity as a lens to peer into the early universe. Since gravity affects everything with mass or energy, and photons of light have energy, gravity can bend the path of light as it moves through space. When just the right collection of objects pile together between us and some distant galaxy, the collected gravity can act like a lens to focus light in our direction. Light that normally would have journeyed elsewhere. Using the very large array of radio dishes in New Mexico, scientists have explored the region of the sky around the galaxy cluster MACJ 0717.5 plus 3745, looking for distant systems magnified by gravity. And they found one. The impossibly named galaxy, VLA HFF-J071736.66 plus 374506.4, has been magnified 6 times by the cluster's gravity, allowing astronomers to see an ancient galaxy like nothing previously seen. According to Eric Jimenez Andrade, the magnification provided by the gravitational lens, combined with extremely sensitive VLA imaging, gave us an unprecedented look at the structure of a galaxy 300 times less massive than our Milky Way at a time when the universe was less than half its current age. This is giving us valuable insights on star formation in such low mass galaxies at that time and how they eventually assembled into more massive galaxies. This work is described in a pair of papers appearing in the Astrophysical Journal.
From the edge of the universe, we now jump to the surface of an asteroid near and dear to our hearts. Back on October 20th, 2020, the OSIRIS-REX mission planned a gentle boop of the surface of the asteroid Bennu, and the plan was to grab a bit of rock as it bounced away. Things didn't exactly go as planned, and instead of a gentle boop, the spacecraft dramatically plunged into the surface before pulling away with more rock than it ever expected to pick up. now in a presentation by Dante Loretta at the Lunar and Planetary Sciences Conference. We learned that plunge was a lot scarier than we knew. According to his abstract, 6 seconds after making contact with the surface, the spacecraft fired its thrusters and initiated the back-away maneuver. At this point, the spacecraft still retained a downward velocity of 4 centimeters a second. The back-away thrusters fired for 3 seconds before the downward velocity was arrested and the spacecraft began to safely move away from Bennu. At this point, the TAGZAM head had penetrated about 50 centimeters into the surface without much resistance. Put another way by Paul Byrne on Twitter, the spacecraft would have continued meters into the asteroid if it hadn't fired its gas canister. This asteroid is more the consistency of a pile of styrofoam balls on Earth than a rubble pile, as we described it. We are so lucky things went as they did, and I can't wait to get samples back to Earth in September 2023.
The number of talks about worlds with hidden oceans would almost make me believe Bennu is the only dry object in the solar system. It's not, but anyway, if researcher Alan Stern is right, the ocean worlds, including Pluto, Europa, Triton, and many others, are actually better places for life to evolve than our own planet Earth. According to a release on his work, worlds like Earth with oceans on their exterior are also subject to many kinds of threats to life, ranging from asteroid and comet impacts to stellar flares with dangerous radiation to nearby supernova explosions and more. Frozen ocean worlds, on the other hand, with crusts tens of kilometers thick, can protect any life they harbor from all those threats. Currently, we don't have the ability to sufficiently sterilize a spacecraft or dig efficiently through ice, which means we can't send a mission to look for this kind of life. And even if we couldn't do it without risking killing off that life with our world's germs. Still, I maintain hope that within my lifetime, or the next generation's lifetime, we will develop the needed tech, and some still to be imagined robot will go looking for life in alien oceans. After this break, we'll be back to discuss the possibilities of water and life on Mars. For decades, we've said that Mars lost all its water to space. It turns out, though, that we were wrong. In a new paper published this week in Science and presented at the Lunar and Planetary Science Conference, researchers have announced that between 30 and 99% of Mars's ancient water is not lost in space, but rather locked up in minerals on the red planet. Let's go back to the beginning. Billions of years ago, Mars had enough water to be covered in an ocean somewhere between 100 to 1,500 meters deep, about a half of our Atlantic Ocean in volume. That water was only on the surface for 1 billion years, though, and then Mars looked as dry then as it does now. Now, the previous hypothesis was that the water evaporated and escaped into space due to Mars's low gravity. And some water molecules definitely did that. However, the scientists evaluated the amount of water on Mars in all three forms, ice, liquid, and vapor, and analyzed the current atmosphere and crust. So what were they looking for? Here's where a little chemistry comes in from the press release. Water is made up of hydrogen and oxygen, H2O. Not all hydrogen atoms are created equal, however. There are two stable isotopes of hydrogen. The vast majority of hydrogen atoms have just one proton within the atomic nucleus, while a tiny fraction, about 0.02%, exist as deuterium, or so-called heavy hydrogen, which has a proton and a neutron in the nucleus. That lighter weight hydrogen would escape more easily into space than the heavier deuterium, and the difference in escape rates should leave a signature called the deuterium to hydrogen ratio. If all or even most of the hydrogen escaped, the Martian atmosphere's DH ratio should lean heavily toward the deuterium, but the measured value doesn't match the expected value. Okay, then, let's look at the rocks. Water erodes rocks, but it also causes chemical weathering that creates clays and various hydrous minerals. We can find evidence of these processes here on Earth, so it had to have happened on Mars as well. The difference is that on Earth, we have plate tectonics and volcanoes that recycle all that locked up water back into the mantle and then into our atmosphere during eruptions. Mars seems to be mostly inactive when it comes to volcanoes, though. So the water that gets locked up in minerals stays locked up. Co-author Bethany Ellman sums the work up. Atmospheric escape clearly had a role in water loss, but findings from the last decade of Mars missions have pointed to the fact that there was this huge reservoir of ancient hydrated minerals whose formation certainly decreased water availability over time. One of the best parts of this research was how it used data from all kinds of sources: meteorites, telescopes, satellite observations, and samples from our army of rovers that they analyzed. Now we just need perseverance to find us some evidence of past life. Or perhaps current life. In a comment published this week in Nature Astronomy, Dr. Natalie Cabral from the SETI Institute hypothesized that life on Mars may not be as extinct as we currently claim. Instead, it may be abundant but underground. As I noted earlier, Mars's water disappeared early on in the red planet's history, leaving behind a dry world, at least on the surface. But water isn't the only factor important to life. There are other factors, like the thin atmosphere, UV radiation, salt content, moisture levels, and temperature fluctuations that can all affect the potential for life. As Dr. Cabral explains, you can walk on the same landscape for miles and find nothing. Then, maybe because the slope changes by a fraction of a degree, the texture or the mineralogy of the soil is different because there is more protection from UV, and all of a sudden, life is here. What matters in extreme worlds to find life is to understand the patterns resulting from these interactions. So, instead of following the water, she suggests following the patterns. We need to examine Mars as an entire biosphere, questioning where life could be now, but also how it would have gotten there. Back when Mars was wet, it had rivers and oceans, as well as the wind and dust storms we observe now. All of these mechanisms could have helped distribute microbial life forms around the planet. And now, that life could be thriving below the surface. Remember, however, that we said a few episodes ago that Percy is not going to look in places where life could still be. We want to be careful not to contaminate those places. But we're planning to send humans to Mars, so we need to figure out how to sample those places before that happens. Quite the conundrum. We'll keep you updated as decisions are made and missions are planned. Up next, Pamela is going to talk about her favorite subject some more: volcanoes. Stay tuned.
Water isn't the only liquid in the solar system. As we mentioned Tuesday, we were deeply amused to find Io with its lava reservoirs listed as an ocean world. In a way, this kind of means Earth has both surface oceans of water and subsurface seas of magma. And that magma likes to escape. Back in July 2018, residents of the Big Island of Hawaii were sent fleeing from their homes as the Kilauea volcano split open subdivisions and casually oozed lava over everything. This particular volcano is one of the most active and most studied in the world, but it still has a lot of surprises to offer. This particular eruption was the stuff researchers dream of. And then graduate student Penny Weiser flew halfway around the world to take advantage of all this volcano had to offer. Using samples of minerals formed during the eruption, she and her team worked to understand where in the Earth this molten rock had originated. In our standard textbook diagram of a volcano, a single magma chamber feeds eruptions. Kilauea, however, breaks the mold and actually has a shallow reservoir, 0.5 to 2 kilometers beneath its eastern rim, and another 3 to 5 kilometers deep near its southern crater rim. Each reservoir has a different composition reflecting the amount of gas at that depth and the different mixes of chemicals. Early measurements that looked at gases trapped in volcanic glasses had thought the 2018 eruption came from the shallow reservoir. But Weisner went the extra step of also studying the olivine crystals that formed in the fresh lava. Here, she saw structures that looked like they came from the deep reservoir that was responsible for eruptions in the 1960s and 70s. This hinted that the 2018 eruption also came from deeper down. In December 2020, another eruption, this time actually from the shallow reservoir, occurred. And like so many familiar eruptions, it simply fountained and oozed beautifully. This raises the question, was the lower reservoir responsible for the home-destroying habits of the 2018 eruption? Only time and more eruptions will tell. But each new measurement will help us get closer and better at linking chemistry, structure, and the severity of the erupting outcome. Predicting when volcanic eruptions will occur is one of those things we just don't do well. Yet. Currently, I'm standing for the Icelandic Meteorological Office and its isn't it coverage of a possible upcoming eruption on the Reykjanes Peninsula, just far enough away from Reykjavik to make things interesting but not dangerous. For a while there, it looked like things were gonna blow. But we're now seeing things calm down. And while alerts remain in place, the situation is being reassessed with an update due after the time of this recording. To try and understand when we need to worry and when we can ignore rumbling mountains, geologists are turning to thermal data. In new research appearing in Nature Geoscience, Tereso Garona and colleagues present a 3.5-year analysis of the temperatures around various volcanoes before they erupted. 90% of these eruptions weren't predicted. But Garona discovered in historic data that the ground temperatures around the volcanoes increased by as much as 1 degree Celsius in the 2 to 7 years preceding the eruption. This doesn't tell us exactly when an eruption is coming, but it does spotlight which mountains are worth worrying about. The land isn't heated directly by the magma. Rather, the rising magma releases huge amounts of water vapor, carbon dioxide, and sulfur dioxide gas that transfers heat while in some cases vaporizing groundwater. The heat released by these gases and vapors heats the land as it cools and escapes. According to Florian Scheiwander, deputy chief of the NASA Ames Earth Science Division, Garona's research has shown that satellite data can be used to detect a volcano heating up years before an eruption. We didn't know that before. Hopefully, this kind of information will make it easier to forecast places not as volcanically covered as Iceland, which I will continue to stan in hopes of harmless but pretty eruptions. After the break, we're going to talk about Saturday's equinox and what this means for the seasons and the sun. Stay tuned. Hello and welcome back. And now we have our regular Thursday segment, What's Up? And this week, it's not so much a case of what's up as what's aligned. On Saturday, March 20th at 4:48 p.m. Central, that's 5:58 p.m. Eastern, the Earth, the Sun, they're going to align with the tilt of the Earth's axis exactly at a right angle to the Sun. This is going to allow the Sun to shine straight down on the Earth's equator. Our planet is tilted 20 some odd degrees, and that tilt stays aligned with the stars as the planet goes round and round the sun. This means that back in December, which really honestly feels like yesterday, I'm not quite sure how it's the equinox already. Anyways, back in December, which feels like yesterday, The north pole of the Earth was pointed exactly away from the sun, following that 20 some odd degree tilt, and we had our shortest northern day of the year. South had a longer day. Saturday, with that tilt perpendicular to the sun, we all get the same amount of day and night. Both poles get illuminated for one special day. And if you want to, you can actually go outside and do a little bit of work to figure out exactly where you are on the planet with a stick and a ruler. So here's what's going on. Right now, we are not in winter. In winter, the pole points away from the sun. We then travel around the sun, and then we end up with the pole at a right angle to the sun and the sunlight straight down on the equator. Now, if the sun is straight overhead on the equator, this means that if there is a well exactly on the equator, sun will go straight down that well. But if you are north or south of the equator, the sun won't be straight overhead. And if you stick a stick into the ground, that stick is going to create a shadow. And the length of that shadow related to the length of the stick is going to tell you what angle you are away from the equator. Now, if this sounds a little bit familiar to you, this is because Erasthenes of Cyrene, which is now Shahat in Libya, when he was a young scholar, he heard tales of a well along the Nile where on one day a year, not an equinox, this was solstice, that other day we talked about a minute ago, the sunlight on that day shone straight down the well, just once. And he realized that by traveling around the planet and knowing exactly how far he traveled, exactly north of that well, he could stick a stick in the ground, do geometry, and measure the size of the Earth. And he did. This was our first understanding of exactly how large the Earth is, and it was measured in how far a camel travels. Because that stick he stuck in the ground, he did that in Alexandria. And you can travel by camel from that well to where he worked. So, since you know where the sun is on Saturday, go outside, stick a stick in the ground, wait for its shadow to get its absolute shortest. That's the moment when the sun is closest to straight overhead. Noon is a lie. Noon is based on Greenwich and time zones. Wait for that shadow to get as short as it can get. Measure it. Measure the length of the stick. Go to CosmoQuest.org and find out how to do the geometry. And you can figure out exactly how far north or south of the equator your stick happened to be stuck in the planet Earth.
One of the more awkward parts of pre-recording this show is we expect there to be breaking news today on Biden's appointment of Bill Nelson as the next NASA administrator, as well as a test firing of the SLS rocket at NASA Stennis. Whatever happens, we remind you that space is hard and funding space is political. More on these stories tomorrow, but before you go, I just want to remind those of you old enough to remember a random politician flying on the space shuttle back in 1986. That politician was then Representative Bill Nelson. 10 days after his return to Earth, the Space Shuttle Challenger was lost, and the path of random politicians to fly to space was closed.
This has been The Daily Space. Join us again tomorrow when we'll tell you more about whatever happens with the SLS test firing and updates on Bill Nelson's possible appointment. If you've enjoyed this show, check out all we have to offer over on CosmoQuest.org. And remember, we're a nonprofit show. If you'd like to support us, you can do this at patreon.com/CosmoQuestX. Thanks.